In this example, we're going to think about dealing with reactions that have unconventional reaction orders. So take this reaction, for example, where any old reactant A reacts to become some products. Now, suppose that we carry out an experiment and show that doubling the concentration of A results in a square root of 2-fold increase in the reaction rate. What is the order of this reaction with respect to A? Well, if everything else is left constant, because we know we can write a rate law expression as the rate is equal to a rate constant K times the concentration of A, our reactant, raised to some power that we've yet to determine. If everything is held constant in this reaction's rate law expression, except the concentration of A and the rate, then we can determine the overall sensitivity of this reaction's rate to the changes in concentration of A. In this case, the reaction changes by a factor of the square root of 2. And that occurs when the concentration of A changes by a factor of just 2. So what's the sensitivity of this reaction? What's the order of this reaction, or the exponent m's value? Well, you might recognize that in order to get the square root of 2 from 2, we have to raise 2 to the 1/2 power. So in this case, the order of the reaction with respect to A is fractional. It's 1/2. But what happens if we had no earthly idea how to deduce this fractional exponent? Well, we could still get the same answer by applying rules of logarithms. So let's alternatively solve this problem using logs. So we're going to use logs to do the magic of math for us. Let's assume we didn't know anything at all about the solution to this problem. I'm just going to get rid of our 1/2 solution for now. And instead, we were faced with this equation where we have to solve for m. To solve for m, we could arbitrarily take the log base 10 of both sides of this equation. And what we do to one side, we do to the other. Why do we decide to take the log base 10? Well, the base is arbitrary. We could take the log base e if we wanted to, or the log base 1, or the log base 2. But we choose the log base 10 here just because of convenience. Now, how do I solve this problem? Well, I could recognize that any time that I've got an exponent in a quantity for which I'm taking a log, I can write that exponent as a multiplying factor out in front. So I can rewrite this expression as the log of the square root of 2 is equal to m times the log of 2. Now I can solve for m by dividing both sides by the log of 2. What does this give me if I punch it into a calculator, whether I punch in log base 10 of square root of 2 over log base 10 of 2, or the natural log of the square root of 2 over the natural log of 2? In any case, I get this result, that m is 1/2. And this is a technique that we could use to solve for any order of reaction with respect to any reactant.